These children have been doing origami since they were 2 or 3 years old, so it's not surprising they show a great deal more expertise than I do. But origami is more than a creative pastime. It also teaches dexterity and logical thinking, and sometimes that can lead to great things. Professor Koryo Miura loves origami. And believe it or not, he's using it to solve problems that have some NASA scientists tearing their hair out. The problems of designing and packaging hardware used in space. Space structures must be light, strong and compact. And at the same time, they have to be reliable, accurate and easy to deploy. That's a tall order in anyone's language, and people spend thousands of hours on computers trying to fill it. But Professor Miura, who works at the Space and Aeronautical Science Institute outside Tokyo, has designed solar arrays and space antenna. And he's done it just by folding paper. This design was the inspiration for his solar array.
We need a very large solar array for the generation of power.
What was needed was a way of packing the array of solar panels, which are used to generate power in space, into a small launch vehicle. Professor Miura started thinking about the problem by thinking of the array as a flat piece of paper, which needed to be compressed into a small package.
This is a solution of problem, but it's not smart at all.
Looking for a smarter solution, the professor studied various origami designs and found a vital clue in this collapsible origami cylinder.
You can see this pattern everywhere, like pattern in this.
You see it in folds?
Yes,
naturally.
folding, yes. This is the natural shape of folding cylindrical shell.
He analysed the folding method and found that when he used it to fold two curves, or partial cylinders, in opposite directions, the flat area where the curves merged was transformed into a series of parallelograms. He then tried folding his flat sheet of paper into rows of parallelograms, and eureka! It worked.
Everywhere in the surface composed of the parallelogram, and the repetition of this pattern to this direction and both directions. And you can pack it very smartly.
Professor Miura went on to draw up a detailed design of the solar array, which, when deployed, will look something like this. In the process, he realised he'd also stumbled onto a very smart way of folding maps. Most navigators admit to having trouble getting a map to refold, but Professor Miura's parallelograms will only refold one way, and this is it. The Olivetti company has now produced a tourist map of Venice using the technique. There's no doubt the Italians have an eye for good design, but perhaps not Tokyo University's conservative academics. Professor Miura had a tough time convincing them that his design deserved serious consideration. When they dismissed his origami model, he asked one of his students to compute the problem using a high-speed computer. The student arrived at this solution months later, a contour map closely resembling Professor Miura's origami map. So you really had to start with the answer and go back to find the question.
That's right.
Professor Miura's solar array will be put to the test in 1995 when it's launched into space on board a retrievable space platform, like this full-scale model. If all goes well, all 36 square metres of the array should fold out from one section of the module as easily as Professor Miura's folding map. And then it should fold back in again just as easily. 1995 will also see the launch of another Miura brainchild, the tension truss antenna. The 10-metre wide truss will be the largest antenna in space. The greatest challenge was finding a way of deploying the mesh reflector so that it would immediately assume a perfectly rigid and symmetrical shape. This time the solution was an arrangement of 6 support masts which gradually extend and telescope out from a central mast. These spread the reflector like an umbrella, and the mesh is then made taut by cables tied to a support structure underneath the main reflector. The origami professor is now turning his attention to the next generation of space stations. He says they will be ultra-lightweight and consist of instruments mounted on adaptive structures, with the critical task of positioning the instruments. But whereas today's support structures are often clumsy with limited manoeuvrability, Professor Miura's will be compact and able to move in every direction at the touch of a button, like his space worm. The worm was inspired by silkworms, which are very flexible but can also retract into a very compact cocoon. Professor Miura's worm achieves similar flexibility through 27 independent actuators. When it's deployed in space, it could be used as a support structure for an antenna and pointed at different stars, or it could be used to manoeuvre the same antenna around other experiments on the space station which might otherwise obstruct its view. For Professor Miura, folding paper is definitely not kid stuff. He says origami teaches people to look for geometric solutions rather than algebraic ones. And since geometry is more intuitive than algebra, it produces more practical designs. One of the professor's proudest design achievements is already far away in space, but he keeps a model of it at his home. The simplex mast imitates the helical structure of DNA. Unfurled, the mast consists of 3 flexible rods with a cable running through the centre. So this is all that's moving, the cable?
Yes.
It's just pulling it down. Pulling on the cable transforms the straight rods into a helix, but the helix only appears in the transition phase. Eventually, the flexible rods form a coil, which is easily and economically stored. Professor Miura's 2 simplex masts displayed their helixes briefly on board the Akabono satellite when they unfurled in space in May 1989. And soon we may see origami used to explore new frontiers in mathematics. Already it's solved problems deemed impossible by classical Euclidean geometry.
For example, this is the given angle.
Trisecting an arbitrary angle, something the textbook said couldn't be done, is easily accomplished using origami. Origami works where the old compass and ruler failed because, like high-speed computers, it employs a large amount of processing power.
It's a 3 equal angle divide angle. Very simple. In the textbook...
In fact, simultaneously folding 2 parts of a piece of paper, as the professor does when he trisects the angle, is a form of parallel processing.
Putting this point to this, then simultaneously we put this edge to this hole. That means that these 2 processes can be done simultaneously, method used by a supercomputer.
But Professor Miura is thinking of more than trisecting angles when he says origami can take us beyond Euclidean geometry.
We can establish another geometry beside the Euclidean geometry.
And you think it will help us solve the problem of the 4th dimension?
Yes, and the 4th dimension and the 5th dimension.
How it can do that is still being determined, but Professor Miura is convinced origami holds the key. And just as he's solved problems in another realm by folding paper, he thinks others can do the same.